Hey everyone, today I'm going to be talking about the Secure Multiserver OS project. So this is something that we've been working on internally at TS for a while now, but I think this is the first external talk we've done on it, so I hope to shed some light on it. My name's Alwin, and I'm mainly focused on the engineering side of things, and the other key people involved are Kevin Gernot, who steered the project, and Craig, who's looking into the verification aspects. So let's get right into it. So the motivation for SMOS boils down to a pretty simple sentiment. Modern operating systems are fundamentally insecure. Seeing as this is an SEL4 summit, I probably don't have to do much to convince you of this, but for those that aren't so sure, I'll try and explain why. Let's do a case study of Linux. Linux has somewhere around 25 million lines of code, and it's constantly growing. There's new bugs and vulnerabilities of all of this growth, particularly in drivers, where this is where most of the new code is added. Bugs are inevitable, but the monolithic nature of Linux makes these much worse, because you can compromise fundamental kernel subsystems or even have arbitrary kernel mode code execution because of a bug in a random driver. Now, I'm picking on Linux a bit here, but the Microsoft and Apple worlds aren't that much better, as we can see from the triangulation exploit that went unnoticed on iPhones for years, or the recent CrowdStrike debacle on Windows, which took out critical infrastructure in airports and hospitals. If we can't even defend operating systems from ourselves, how can we stand against the sophisticated attackers of today? So the idea that mainstream OSs are insecure isn't a new one, and people have been trying to fix this for the past 50 years. I don't have time to go through all of the attempts, but I'll talk about just the ones that the NSA have worked on. They started with DT-Mark, where they tried to make a secure OS on top of the Mark microkernel, but they found that Mark was too complex and slow, so they decided to make their own microkernel with a specific focus on assurance. This was in the DTOS project, but they failed to verify even the implementation of the microkernel, so they gave up on verification of components and instead decided to implement the similar Flask framework on top of the Fluke microkernel. The timeline gets a little bit hazy here, but eventually they dropped microkernels altogether and they just said, screw it, let's just do this in Linux. This gave us SE Linux, which is probably one of the most widely used secure OSs of today, but it's really not that much better than stock Linux, especially against kernel-level exploits, because at the end of the day, it's just another module in the all-encompassing blob that is Linux. So fast forwarding to the present, we still don't have a secure OS, but what we do have is SEL4, which is a secure microkernel. We know that SEL4 has functional correctness and is able to uphold confidentiality, integrity, and availability properties in a correctly implemented system. The question that SMOS is trying to answer is how we can use SEL4 to build a dynamic, general-purpose, and provably secure OS. Now, we're not the first ones to try and use a microkernel to build a secure OS. What gives us hope that we won't fall into the same fate as something like DTOS or Flask? So there were two key factors that made past attempts fail. One of the prerequisites for DTOS was a verified kernel, and at the time this was considered impossible, yet here we are today with the verified SEL4. Now, just a verified kernel isn't enough. We need to extend our verification to user space, since at the end of the day, the kernel is just a small, albeit very critical part of a complete secure operating system. But the verification of SEL4 shows that verification tools have come a long way, and the ongoing verification of user space in projects like LionsOS and Crytan's work give us hope that we can apply the same principles to SMOS. The other issue with microkernel-based operating systems of the past has always been performance. So this is if it's a secure OS or not. Like verification tools, hardware has also made a lot of progress, and unlike Mark, SEL4 is demonstrably fast, with projects like the SDDF showing that excellent performance is still achievable. So what are the goals of SMOS? Our first goal is a dynamic architecture so that we can target general-purpose systems. Most existing frameworks for SEL4 are for the embedded space, where a static architecture, where you predefine all the components and all the interactions they can have with each other, is good enough. But the problem we're trying to address is the insecurity of mainstream operating systems, which don't have these kinds of constraints. SMOS needs to have a dynamic architecture so that it can one day be as general as something like Linux, where a user can download arbitrary executables of the internet and run them at will. The next thing we want is policy agnosticism. We want secure operating systems, but we recognize that there isn't a one true policy that works best for every single use case. Our framework should be able to support whatever best works for the situation, whether this is Bell LaPadula, a Unix file system model, or some complex information flow policy. Regardless of the policy, we want to make sure that our enforcement is verifiably correct and that the policy is always upheld. And finally, we want to do this without a major hit to performance compared to mainstream systems. Okay, now that I've gotten out of the way the goals and motivations of SMOS, I mainly want to show you what the policy enforcement mechanism that we would use looks like, but first we need to set up a sketch of how a system is composed in SMOS. So the initial task of the system is known as the root server, and its responsibility is to bootstrap everything else and then act as the main memory manager of the system. Currently, it also contains the connection server, which is responsible for the connection architecture of the system, and the security server, which is a centralized store of all the system's security state and policy logic. All of our other processes start off connected to the root server, which provides the base services that they need for bootstrapping, and a process that wants to be a server can call into the connection server to be published under some name, after which it can be connected to by a client who wants to use its services, at which point a connection between the two will be established. So with that simple sketch of a system, I want to talk about how the system's policy is enforced. So let's make things a little less abstract and say that our object server is a file server. So our client is going along and executing, and it needs to read a PNG file that's provided by our file server. So it calls into the file server and asks to open this file. In most security policies, opening a file would be considered a security-sensitive operation. So this means that the file server has to consult the security policy of the system. As I said before, all the system's security state and policy logic is contained in the security server. So it has to make some kind of query. But you might be wondering, what does this query look like? So one thing that's important to understand is that all subjects in the system, which are actors, and all objects, which are things being acted upon, have something called a security ID or SID associated with them. These are opaque identifiers from the perspective of the file server. They don't really mean anything, but they are linked to the security state of the system. So what the file server has to do is find the security ID of the subject in this operation, which is the client, and this is provided by the connection architecture, and the SID of the object, which is the file. Where it gets this from depends on the implementation, but in this case, it'll probably be stored with the file's metadata. Using these, it has to construct a query that has the details of the operation and the SIDs involved, and sends this off to the security server. So now that the security server receives this message, as I said before, the SIDs are linked to the system security state. And what it does is decode the SIDs to get some policy-dependent security context, which allow the security server to perform whatever checks and updates are needed before it can return the policy decision. Our goal with this kind of design is to make this object server's policy agnostic. So the change in policy just means that you have to change out the implementation of the security server, and you don't have to do invasive changes to all of your object servers. Continuing with our sketch example, let's say the policy is Bella-Padula, which has a read-down clause. If our client has a top secret classification and the file has a secret classifications, then this open with read operation is permitted, so this is what the security server would return back to the file server. So after receiving the outcome, the file server will either continue with opening the file, as in our case, or it'll reject and return the failure back up to the client. So one thing that you might have noticed in this whole process is that the whole thing kind of hinges on the file server correctly invoking the security server. So this is true, and we call servers that we trust to do this a trusted server. We currently assume that this is the case, but obviously in a real secure OS, this isn't satisfactory. We need to ensure that this is true, which is something I'll talk about in a moment. So, and with this policy outline of what the policy enforcement looks like, we have enough background to explain why we think that such a design can be made secure. So what does security actually mean in the context of an operating system? So one definition that's pretty popular in the certified OS world, and the one that we use, is that a secure OS satisfies the reference monitor concept, and this has 3 criteria. The first is complete mediation, which says that all the security-sensitive operations are mediated by the system. The second is that the policy enforcement mechanism of the system is tamper-proof, so that it can't be modified or bypassed by untrusted processes. And the final condition is verifiability, which says that the policy enforcement mechanism is small enough to be verified in some regard. So for SMOS to satisfy the reference monitor concept, we've identified that there are 3 key problems that we have to solve. And to walk through these, I'll expand the previous system a little bit. First, I'll add a new client to the file server, which makes it a shared file server. Then I'll extend the file server with a block subsystem, which is, I guess, the backing store of this file server. And then we'll add an I2C subsystem, which is another subsystem that's there, but it's less security critical than something like our shared file server. So the first challenge we have to address is to do with the correct implementation of policies. As I mentioned before, all the security state and policy logic is contained in the security server. But what this means is that for the system to be secure, the implementation of the security server has to actually correspond with what the policy prescribes. The difficulty of this will really depend on what policy you're implementing. Something like Bella-Padula with fixed classifications on compartments is relatively easy to reason about, whereas a complex dynamic policy, like those dealing with information flow between components, is much more difficult. The second problem stems from my previous assumption that I mentioned, that trusted servers always correctly invoke the security server. Although the policy logic and security state is all contained in the security server, trusted servers obviously play a crucial role in upholding the security policy of the system. If they don't invoke the security server correctly and reject if the security server rejects, the whole security story falls apart. So we need to verify that the policy enforcement mechanism is invoked for all security-sensitive operations, and if it's rejected, our trusted servers also reject them appropriately. And the final problem is that even if our trusted servers invoke the policy enforcement mechanism, if they're incorrect or have vulnerabilities, it's still possible for them to violate the system policy. What this means is that we have to eliminate bugs in our trusted servers and ensure that they behave according to some specification of their correct behavior. One advantage we have is that each component is self-contained and modular, but full-scale verification to the scale of something like SEL4 is still completely impossible. But one good thing about the multi-server approach that we use and the verification of SEL4 is that there's no need for a one-size-fits-all approach. Our more critical subsystems, like our shared file server and the security server in this case, can undergo stronger, more time-consuming verification methods, while less security-critical subsystems, like the I2C, or ones that don't directly interface with clients, but communicate with more strongly verified components, don't need to go through so much verification. What this means is that even though all components aren't equally trustworthy, policy violations can be contained. So if a malicious client compromises our fairly security unimportant I2C subsystem, they can breach the I2C part of the policy, but there's no easy path for them to turn this into a breach of the more strongly verified security server or trusted file server. So in terms of implementation progress, we initially did a C prototype where we implemented a bunch of the abstractions we want to use and a few simple sketches of policies. Recently, we did a fresh start in Rust using Rust SEL4, which Nick will be talking to you about tomorrow. This started a few months ago, and it's more lean and principled, but it's not quite on feature priority with the C implementation yet. And on the verification side, Craig is working on modeling some access control-based systems with policies specifically related to information flow to make sure that we can represent these systems and enforce these policies with the mechanisms and APIs that we provide in SMOS. That's all. Thanks.
Okay. Thanks, Alwin. Questions? We have time for one question.
So the general way of describing the access relies on having identifying each object and each agent in the system.
Yep.
Is the description of the policy static, and do those identifiers have to be statically defined?
Not necessarily. So I guess the way it would work is that you would define the policy of the system at build time probably, but the policy can evolve as the system evolves. Like you should be able to change the policy, like add to the policy, if that makes sense.